Hey guys, it is Friday, March 26th. Make sure you fill out the attendance link right here so we can give you credit for attending the lesson for today. Checklist items. Your test was today, so make sure you complete your test and you turn it in on SchoolNet. After the test, we took notes on the beginning of our physics unit, which is forces in motion. So make sure you get your notes done. And then also your human body vocabulary was due today. So make sure you get that turned in as well because we will be grading that. Your code for your test should be in Google Classroom. So you need to check your teacher's Google Classroom to look for your SchoolNet code so that you can take your test. So I'm going to go ahead and start talking about your forces and motion notes. Just remember that all of your notes, the highlighted words are the answers to go into your notes template, okay? So it shouldn't be hard. The highlighted areas are the parts that go into your notes. So keep that in mind if you're having a hard time finding what's supposed to go in what section. So let's start with motion. Motion is a change in position over time. So if something is getting closer to another object, if it's getting further away from an object, that means it's changing position, so it's in motion. It can be described with a reference direction such as north, south, east, west, up, or down. So when you're describing motion, you're typically going to use directions. Now, how do we know if something has moved or not? Well, we use something that's called a reference point. A reference point is something that's not moving. So you have to pick an object that is not moving because you're going to use that object to see if you're moving, right? So whether you're getting closer or further away from that object, that lets you know if you're in motion. If you stay the same distance away from that object, then you're not in motion. So a good example would be when you're riding in the car. And let's say you see a house. A house is obviously not in motion, has a foundation, it's on the ground, it's not moving. So a house could be a reference point. If your car and you are getting closer to the house and then further away from the house, obviously you're in motion. But let's pretend there was a stop sign and you're stopped, then your motion hasn't changed from the house, which means you are not moving. The house in that situation would be our reference point. So with a reference point, the motion of an object is always judged with respect to some other object or point, which would be our reference point. When an object changes position over time, which means it gets closer or further away from something, that means it's in motion. So like this car, you could use these trees as a reference point. He is getting closer to the trees, he is in motion. The trees would be the reference point. So let's talk about the difference between speed and velocity. Everybody considers speed as how fast you're going, and that's pretty accurate. Speed is how fast you're traveling at a given time, right? So here in the US, we use miles per hour. That's how many miles you can travel per every hour, right? But other places use the metric system. So they might do kilometers per hour, meters per second. So you have to make sure you pay attention to your units, first of all, when you're looking at speed. The difference between speed and velocity is that velocity actually incorporates speed. So velocity is also how fast you're traveling, but it also adds in a direction. So if speed is just how fast you're traveling, velocity is how fast you're traveling, but in a certain direction. So a lot of the times you hear things like a meteorologist, when they're talking about a severe storm making its way, they might talk about the velocity of the storm. And they might say that it's moving 20 miles per hour northeast. That's the velocity of the storm because he told you how fast it's going as well as what direction it's moving. Everybody's heard of acceleration before. Most of the time people just think of acceleration as speeding up, and that is an example of acceleration, but there's more to it. So acceleration can be one of three things. It can be an increase in speed, or a decrease in speed, so something slowing down, or a change in direction. So the three pictures on your screen right now, the first picture, the guy is about to release the ball and it will increase in speed. The second picture, you see the ball was hit and the glove is about to stop it, and then the ground is causing friction to slow it down, so that's decreasing speed. And then the third one of the batter hitting the ball, that's about to be a change in direction. That ball was coming straight down. Now when he makes contact, it's going to go straight back out. So that's a change in direction. All three examples are examples of acceleration. So when we talk about forces in motion, we have to define what a force is. A force is just a push or a pull on an object, and here's the key word here, that causes a change in motion. The object has to be changing its motion, okay? So there are a lot of different types of forces. There are contact forces, which we see over here. These are forces that happen because objects touch. So there can be like an applied force where you apply the force and cause it to change direction here, like the person with the baseball bat. There can be a spring force, a drag force, so on and so forth. There are also non-contact forces, and these are going to attract or repel. So these are definitely your magnets, right? Because your magnets can pull things towards it or push things away. And then definitely gravity as well. Gravity automatically pulls things down, and that has no contact involved. So forces are pushes or pulls that can cause an object to change its motion. Friction plays a big role in the motion of an object. Friction is a force that's going to oppose motion, right? It's going to want to slow things down. Friction wants to stop the motion between two surfaces that are in contact. So the amount of friction is going to depend on two things. One, it's going to depend on the roughness of the surfaces. Obviously, there's going to be less friction. If you have a smooth surface, it glides easier, right? But if you have a rough surface, like sandpaper, there's going to be a lot of friction there. It's not going to be as easy to move on. The second thing that depends on friction, or that friction depends on, is how much force is pushing those surfaces together. Are they barely touching? Are they being pushed together really hard? That's very important to consider. So, for reference, the rougher the surface, the higher the friction. Okay? That would be like trying to ice skate on rocks, right? You're not going to be able to ice skate on rocks. There's way too much friction. So the rougher the surfaces, the more friction there is to slow you down. The smoother the surfaces, the more able you are to glide, so there's less friction. Just like in this picture here. There's less friction at point A and way more friction at point B. There's no way this guy's going to be able to ski down a hill. Now, our forces can either be balanced or unbalanced. If we have a balanced force, that means that the object's motion will not change. If it's going at a constant speed, it's going to keep going at a constant speed. The forces acting on it will not affect its motion. If it's stopped, it's going to stay stopped, okay? If you have a balanced force, your net force will always be 0, and we're going to teach you guys how to calculate net force. Forces can be balanced, like I just said, when they're at rest or not moving, or also if they're moving at a constant rate. So let's look here. We have these two little fat cats sitting on this balance beam here, and each one is applying a force of 200 newtons. They are a balanced force. This one's applying 200 newtons. This one's applying 200 newtons. They're the same. So they're not moving. They're not causing a change in motion. To calculate net force, if you have 200 here and 200 here, they're even. You're subtracting. It's a net force of 0. Look at all of these examples over here. This guy's skateboarding. It says he's pushing off with 100 newtons this way, and then it's going 100 newtons this way. 100 minus 100 is 0. He's going to stay at a constant speed unless another force acts on him. This person here, I don't even know what he's doing, so I can't really describe him. We're going to move on to this little toy car. Force pushing the truck, this would be like one person pushing over here, and this would be somebody on the other side pushing the opposite way, and they're pushing with the same force. Because they're pushing with the same force, their net force will be 0, and that force is balanced, not moving. Okay? So we have to graph this motion. Graphing motion is very important. And so we are going to graph the motion. And the first two graphs here show the motion of an object that's at a constant speed. Okay. This specific object is leaving the start and going at a constant speed away from home. This person is having a constant speed back to where they came from. A diagonal line represents constant speed on a distance time graph. The next one shows an object that's not moving. If you ever see a flat line or a horizontal line on a distance time graph, that means that object is not going anywhere. I like to pretend to plug in numbers here on my X and Y axis just to see. So that would be like saying this distance is at, we'll say 5 meters. As time goes on, the object stays at 5 meters. It doesn't move. Move to another time, still 5 meters. Move to another time, still 5 meters. So no matter what, that object's distance isn't changing because it's not moving. So this would be the graph we would see of a balanced force that was not moving. The opposite of a balanced force is an unbalanced force. An unbalanced force pretty much means one object is, or one person is pushing more than another force is. Okay, with an unbalanced force, it can either slow something down or speed it up. So this is a force that definitely is going to change the motion of an object. It's always going to have a force greater than 0. Okay, so when you have an unbalanced force acting on an object, it can change its speed, it can change the direction it's moving, or it could do both. So if you look at this first picture, this shows you forces in the same direction. Let's say these people are moving this piano. He's pulling it to the right. She's pushing it to the right. So they're both moving to the right. That's why you see these two arrows here. They're both moving to the right. She's pushing with 25 newtons. He's pulling with 20 newtons. Since the arrows are going in the same direction, we combine that. So we're going to add 25 plus 20. That means the net force of the motion of this object is 45 newtons, and it's going to the right in the direction of the larger force. Now let's look at an unbalanced force when you have two different objects pulling on opposite sides. So here you have this little dog. He's pulling that rope back to the left, 10 newtons. But this dog wants it too, so he's pulling to the right with 12 newtons. Now, because he's pulling with 12 and he's pulling with 10, you have to subtract the 10 from the larger number, which is 12. So you do 12 minus 10, and you find that this animal is pulling with just 2 newtons more, so it's going to move in the direction of the larger force, which was 12 newtons, and it's going to move to the right. So the net force would be 2 newtons to the right. Okay, so you notice with all of these examples, our net force is no longer 0, it's an actual number because the object is changing its motion. When we graph unbalanced forces, you will see a lot of curves. You're not going to see diagonal constant speed lines. You're going to see curves because unbalanced forces represent those key points with acceleration, speeding up, slowing down, or changing direction. So in the first graph here, you see acceleration. It's like the car gets going and it hits that gas pedal and it really starts going. Okay? The curve going up is acceleration. This one shows the car going pretty good, but then as time happens, the distance is slowing down. So this object's coming to a stop. So this is deceleration or negative acceleration. Pretty much means the object's slowing down. And this last one shows you an object that's changing direction and going back to the home. Okay? So let's talk about Newton's laws. Newton's first law states that an object at rest will stay at rest, and an object in motion will stay in motion unless it's acted on by an unbalanced force. This is also called the law of inertia. Okay? Inertia is pretty much when an object resists a change in motion. It wants to keep doing what it's doing. If it's sitting still, it wants to keep sitting still. If it's moving forward, it wants to keep moving forward. So for example, when you watch this little blue car up here, it's moving forward, but it stops. But the body keeps moving forward. That's because of inertia. The body wants to keep moving because it's used to moving, right? But the car stops. Look at this example up here with the chair. You're about to see a bunch of books fly. The chair hits and stops, but the books keep moving forward. That's because of inertia. It wants to stay in motion. The bottom one, she pulls out the tablecloth to the left, but the girl still is sitting down. That's because her inertia was larger and she remained seated and not moving. Inertia, like I said, is the tendency of an object to resist a change in motion. A cool little trick you guys can do at home is if you have a cup and a little piece of cardboard, you can put a piece of cardboard on top of the cup and put a coin on the top. And then when you pull the cardboard out, you would think that the coin would want to come with you, right? It's on top of the cardboard, but no, the coin goes down. That's because the inertia of the coin wants to keep staying at rest. It doesn't want to move with that paper. That's inertia. Here's an example. Golfing is a good example of the first law of motion. Whenever the golf ball is just sitting on the tee, then it would stay not moving unless acted on by an unbalanced force, which is when the driver hits the ball. So the golf ball would sit on the tee forever if that unbalanced force of the driver didn't act on it. But once the golf ball is actually airborne, it wouldn't even stop unless acted by an unbalanced force. We know there's an unbalanced force that's going to stop it, and it's gravity and air resistance, right? It causes that fluid friction in the air. Newton's second law states a relationship between force, mass, and acceleration. There's an equation here, and it's force equals mass times acceleration. So if you're applying the same force to two objects, an object of larger mass, if you're applying a force to it and it only moves a little bit, that's a small acceleration. But let's say you have a smaller object with a smaller mass, and you apply that same force to the smaller object, you're going to see it accelerate a lot quicker. There's going to be a lot more acceleration to the smaller object, but that's because it's easier to push something of a smaller mass than it is a larger mass. As you can see here, the guy down at the bottom, he's having a hard time pushing this 400 kilogram object using this force, but if he uses that same force with only a 40 kilogram object, obviously it's going to accelerate a lot easier and quicker. Same for this guy up here pushing. He uses a specific force and pushes the first girl, and she swings pretty high. This is obviously a larger mass. He uses the same force. That guy doesn't go as far. Now, this slide just gives you an example using numbers. If you're a numbers person and you really want to see it worked out, you use the equation force equals mass times acceleration. And it's saying if you throw a tennis ball and a bowling ball with the same force, which one will go further? So let's pretend we're throwing it with a force of 20 newtons. The mass of a tennis ball is 1 kilogram. The mass of a bowling ball is 5. Okay, so we have 20 newtons, which is our force. Force equals mass, which is 1 kilogram of the tennis ball, times blank for the acceleration. Well, we know 1 times 20 is 20, so we know the acceleration of the tennis ball would be 20 meters per second. Okay, the next one is the bowling ball. The bowling ball had a much larger mass. It was 5 kilograms, so 5 times what is 20? That would be 4, so the acceleration of the bowling ball was 4 meters per second. It definitely went faster with the tennis ball. So the faster the acceleration, the further the object's going to go. So our tennis ball would travel much further than the bowling ball because it has a lower mass. The third law states that for every action, there is an equal and opposite reaction. Think about when you blow up a balloon and you don't tie it, but you release the balloon. The air pushes down, but the balloon moves up, right? That's an equal and opposite reaction. Same thing for skateboarding. Your foot pushes backwards, but it propels you forwards, right? So that is an example of Newton's third law. Here's another example of Newton's third law, but in nature. So a fish is a good example because it uses its fins and it pushes the water backwards, and then in turn, it propels the fish forward, right? So the action was the fins pushing water back, and the reaction was moving the opposite direction. Same thing for the bird. As the bird pushes down with its wings, that's the action. The reaction is to lift it up higher in the air. So when we talk about motion, it's very important that you be able to define what type of motion is happening when you see a graph. So the shape of a graph tells us what an object is doing. The first graph here Position means the same thing as distance. So these are all distance time graphs except for this last one, which we'll talk about in a minute. So on these distance time graphs, remember when I told you you see a diagonal line? That's going to mean a constant speed, okay? So this first graph shows you that an object is moving at a constant speed away from the starting point. Remember I told you anytime you see a curve, that's going to be a form of acceleration. So this graph shows us that the object is accelerating away from the start, and this object is decelerating, which means it's slowing down from the start. Here's our horizontal line, which means as time goes on, the object is at the same distance and not moving. This one shows us diagonal line, which means constant speed, but this time we're going back to where we came from. This one we see a curve. It's accelerating back to the start. And then this one is decelerating back to the start, or slowing down to get back to the start. And the last one, this graph looks exactly the same as this graph, but you've got to pay attention to what's on your X and Y axis. This time, instead of distance and time, we have speed and time. So let's pretend that this is 20 miles per hour. As time goes on, the object stays constantly moving at 20 miles per hour. That means that's like having your car on cruise control going on I-40, right? You put your cruise control on for 70 miles per hour, and your car continues to go at a constant speed of 70 miles per hour. A horizontal line on a speed time graph means constant speed. So you've got to pay attention to what's on your X and Y axis. The slope of your graphs also give you good information about the motion, because the steeper the slope, the faster the speed. So you can see here in this first graph, that's a really steep line, which means that object's moving pretty fast. We still have a diagonal line in the second graph, but the slope is much less. It's a much smaller grade going up. So this is a slow constant speed. Same for this situation. It's fast. It's a steep line, but you're going back to the start. And then same for this one, except for it's not as steep. It definitely takes a lot longer to get back down. So this is moving at a slower constant speed. This slide tells you to use the graph to match the letter to the correct statement. So this is a distance and time graph. We see object A, B, and C. The object that's moving at a constant speed is our diagonal line, which is B. The object that's accelerating quickly and finishing first, we see that steep line curve, there's A, so it finishes first. And then the object that accelerates more slowly, we have our curve, but it's taken more time to get there, so that's definitely going to be C. This last slide tells you about a graphing story and how graphing stories can help you understand how you should graph. So for example, you can read a story and then graph the motion of the object based on what's happening. So the graph down below is going to go along with this story. Darcy the dung beetle was a happy little bug. One day he decided to take a walk to a nearby dump. He left his home and crawled at a calm, constant pace. So he leaves his home and goes up, constant pace, right? He sat down and remained at the dump and enjoyed his meal most of the day. So that's why we see this flat line. He stopped, he's not moving, he's sitting down, he's eating, right? After he finished, he remembered an appointment with his friend, so he quickly returned back home. So you see this line is much steeper than that line was. So this was his slow constant speed. This is a faster constant speed. Okay? If you guys have any questions about this information, please reach out to your teacher so we can help you. Thanks.